Good morning, students. I was thinking to give this video lecture that I have prepared because this one I already thought to give this lecture on the presentation. So this is online lecture on structural geology. Because before that we studied the basic geology or natural geology. The structural geology is something that civil engineers would come in and would take full knowledge of this, so that whenever they're constructing anything anywhere, the structural geology would provide knowledge for you to look into how the land that you're building on, or the place that you're building on, would react after some time, or would have reacted before, or would provide you any structural knowledge or any geological knowledge that would help you to take your decision wisely. So here we are going on the strike and dip of the strata. Also, we will study about the folds, faults, joints, and unconformities. So let's review what we have done in the past. So as our subject is engineering geology, it's not basic geology, so that's why we have to move forward from the basic geology to the engineering geology, CE 605. So before our holidays and before until now, we have just done a study on the basic geology. So in the basic geology, we went through the creation of the earth. In the geological terms, we had studied 4 or 5 hypotheses that you made in your assignments and made us know what was the creation of the earth. Then we went through the geological time, and that also was a kind of a presentation that you people presented. And if you people have not given the presentation to each other, it would be important for you to give to each other, because that's what we will be having whenever we'll have an exam or any test. The knowledge about the geological time would be needed, and in what time and how much billions of years it took from the creation of the earth till now, or the human species came into being. Then we went to understand the layers of the earth. We understood the crust. We understood the mental their mental transitions, and then the layers which will contain the core and the inner core. So we studied about their importance, and how these layers are there and what characteristics are there in these layers. We also studied about something, if you would remember, about the how did we came to know about the layers of the earth. We studied about the S wave and the P wave. That if you would remember, I give you an example. Then we went through the volcanic eruption, how what comes of the volcano, or the lava, the magma, where it was created, and how it was formed. So we studied all these things, and then we went to the study of the continental drift theory. We came to know what were the theories that made us know that these continents were one part, the Pangea, and then these all separated. And also now, as the plate of the earth, so tectonic plate of the earth moves, these continents or these subcontinents would move with each other, from each other. Then we came to know how one of the scientists was able to deduct how these things are connected. And also we went to understand the that he was not able to answer the question, where it was it floating. And then we came again back to the the model of the layers of the earth, and he came to know that nothing is floating on the ocean, but there was a convection currents in the mantle that made these things move. And after that study, we went through the rock cycle, how the rocks are formed, because in geology, the very important part is the rock. So you have to understand, out of magma comes the igneous rock, and then we came to know from the igneous rocks, either the sediments are formed or it metamorphizes, and then metamorphic rocks are made, or the sedimentary rocks are made. And that's the rock cycle we understood. We studied about the minerals also, what are the characteristics of the different minerals form, and then in the last lecture we went through the igneous rock and the sedimentary rock, and then the metamorphic rock was one of your assignment. So all these things we have covered till now. Let's see what we'll cover next. So the study review ahead, what we'll study now. So, just because of the lack of time, I have divided the structural geology and the engineering properties into two parts. The first part will be covering here now, and the second part will be covering after some time. So, what we'll study about the strike and the dip, and the strata of the strata, and the folds, falls over here, and then the unconformities over here, and their classification and their types. So we'll study that, and then in the next lecture we'll be going through the engineering behavior of the mass rocks and the engineering properties. So the hardness test, or the strength test, or durability test, all these things we'll be going through. This is a part of rock engineering. uh, One of the book I sent you before was about the rock mechanics. So this is a part of rock mechanics actually. So we'll study a little bit part of it, and then in the last we'll be going through the geological explorations and discoveries. How do you go to a place and you explore the geological form, and but before that we have to study the structural geology. So the strike and dip. First of all, before we go any further about the strike and dip, you have to understand that what's the bedding, and how the bedding is formed. So the surface that separates each other successive layers of the stratified rock and its preceding layer. So you can see over here that there are different layers over here, very very nicely shown in this rock form. So these layers are actually stratified and then cemented a long ago, and that makes us know right now how these beddings are made. So the sediments and the sedimentary rocks are characterized by the bedding, which occurs when layers of the sediments with different particle size are deposited at the top of each other. So you can see, and when you go through, if you put a core right in over here, and you take out that core and you analyze each and every layer, you will find these layers actually having a different sediment size, sediment uh, uh, area. The particle size would be different, and each would be actually make you know the origin or the genesis of these rocks. Then the next thing that we'll go through was, these beds range from millimeters to centimeters thick, and can even go to meters or multiple meter thick. So y- this is actually very short span of the photo. We can see the bedding over here uh, in maybe the centimeters, or not more than the meters, but each layers is very visible. So these are the beddings. Next we'll go on the tilted beds. Now the beddings are also tilted sometimes. There are, if you can see, this is not the tilt it's going through. The tilt is this red line over here. You see, this is the tilt of the sediment. You can see that the this these sediments actually were actually deposited in this way, or perpendicular to the red line, and the beds are tilted because of some geological action, maybe the tectonic or seismic action or the long-term tilting made these beds tilted. So these red lines are the tilted beds. So they're tilted at some angle, and you can see all of these are tilted at some or the other angle. Actually, these separations are not geological separations. Actually, these separations are made by the road company or the government, so that this whole rock would not fall. So actually, this is a part of geological exploration also. How to stabilize a rock form or a mountain over here is by separating it layers. We'll study that afterwards. Then let's dive into the terminology of geological terminologies of strike and dip. So first thing is the inclined strata. Inclined strata are the soil of the rock layer that are tilted due to geological action or seismic activity. So you can see over here the strata is inclined, like we said, the tilted beds. These strata is inclined, and this strata actually is inclined due to some geological activity. Then we see the dip. What's the dip? Actually, dip is the angle that it makes with the horizontal surface. uh, Horizontal, if this is the inclined strata, whatever the angle it makes to the true horizontal surface, that's the angle of the dip. And also the dip has a direction. Over here, if we see this symbol, it shows the 18-degree as dip angle, and over here as dip direction. And strike is perpendicular to the dip angle. Obviously the strike line shows actually the the strike direction, or the direction of the slope. It has it has been uh, it has tilted. So then we go through the horizontal surface. Horizontal surface actually perpendicular to the gravitational pull. So you know the gravity is perpendicular to the horizontal surface. It's actually can be recognized as the water surface or water body surface. Anywhere where you put the water will always remain perpendicular uh, to the horizon to the gravitational force. So y- that's what actually the horizontal surface is. Then how to recognize the strike and dip? There are some rules and regulations that to notify the strike and dip of any rock surface or the rock form which is tilted. So firstly, we go along to see the plane making angle with the horizontal plane. So first of all, we see like in the last sorry in the last slide, we saw the horizontal surface, and the angle that is made on the horizontal surface is the dip angle. So over here we have a dip. So we could recognize the dip angle by judging it with the horizontal line, and we have this dip which gives us the dip angle. The secondary, we go to the arrow that defines the dip angle. So over here the dip angle we got, but the direction of the dip actually is towards, let's say, towards east in this example. And so this dip is dipping towards east at the angle. So the way we say it is that this rock form or the tilted bed is dipping in the east direction at an angle of, let's say, 30 or 40. Okay. And then next is the strike. Now like we said, the perpendicular to the dip angle is the strike. So the dip angle actually gives you the direction where the tilt is dipping, and the strike gives you the direction of where the slope is facing towards. So over here, when we see east is the dip direction, for example, the south and the north is the dip, uh, is the strike direction. So how to exactly know is it south or north? There's a rule for this. This rule is called the right hand rule. if the if the dip is wherever the dip is, if you put your fingers over there of your right hand, the thumb that will point towards will be the strike direction. So over here, let's say this is the east. So if you put your right hand like this on this surface, your thumb will face towards the north. So the north will be uh, your direction. Anyway, we we don't have to put our hand always put our hand wherever we go. Uh, so we have these from this one example. We can actually go through all the examples. So if it's east, it will point towards north. If it's north, if you put your right hand, it will point towards west. If it's west, then it will point towards south, and if it's south, it will point towards the east. So actually it's interchanging. And so with this relation, you can go to any point. Like if it's northeast, where will it point towards? So that's actually one of your work that you would do. But this relation, actually the right hand relation, is always used for the strike and depth. Next, after understanding the strike and depth, let's go to another geological structural part, that is the geological fold. A lot of times we have seen this kind of structure, but we have never always understood, or maybe we did not pay any attention that it really is a part of geology that makes you think about how this thing happened. A lot of times we go to the mountain, we see these kind of structure, but actually we are even I was never interested till I studied about it. uh, how these wavy structure is formed. Look at this, how these wavy structure is formed. This was actually the sediment that was once straight. It was never, so the sediment actually never settles. Whenever you put the water and you put the dust or the what put some sand over there, the sand will never settle in this way. The sand will settle always in a straight line. And that's why how these structures, when when cementation happened, when stratification happened, how the structure actually came into being is one of the very important part of civil engineering. And more than that, it's a part of mechanics. And that's why we study rock mechanics. Anyway, these structure is called the folds. The fold arise as a result of tectonic pressure and the stress in the rock, and rather than fracture, they fold. So actually over here you see the fracture point. Anything, if you hold anything in your hand and you try to break it, firstly it will actually de- deform, then go to the plastic elongation or plastic strain with the stress increase, and then it will fracture. But over here it says then rather than fracturing, they fold. That means that this has been gone through the long term loading. What's long term loading? Actually, anything, if you uh, put a stone, a big stone on the tree on its one side, the tree, if the pressure is too much, the tree will fracture, it will come down. But if it's not too much, but it keeps on pressuring it, it will deform in a way that its shape will change in the same. So if after that also, if you remove the rock, if you remove the stone from the tree will have or retain that shape, because that now has become its original position. Same thing we understand by uh, over consolidation also, or the things that we study in geotechnical engineering, in soil engineering, the over consolidation and normal consolidation and certain things like that. So these things, actually the pressure over here is actually the constant pressure, and in the long it's a long term pressure. So rather than fracture, these rock folded itself. Actually it changed its molecular composition and retained this kind of shape. They are easily visualized by the loss of horizontality of the strata. The fold is a bending of the rock of the Earth's crust. So look at this, wonderfully folded. Next thing we go through is some terms in the geological fold. So over here we see a folded rock, and whenever we look at the folded rock, there are some characteristics that we have to firstly define, and then only we can understand what kind of fold it is, because before we go in any of the type of the fold, we have to understand is what its terms are. So there are many. So let's just read a little bit of this. On many folds, a line joining point which has curvature. Curvature is greatest can be detected. This line can be either straight or curved. It has been termed as hinge. Okay, so the highest curvature over here over here in this place is this point. So this point actually is the hinge. You always understand about the hinge in structures, structural classes. What's the hinge? The place that it folds. So over here is the hinge, and this place is the hinge, and then this is the hinge line. Hinge line is also the strike line. You remember, going back to this, if this is the hinge, or if it has been folded like this, then this is the hinge line, and hinge line is parallel to the strike line. So strike line is parallel to the hinge line, and that's why these things are the same. The hinge line is the strike also. It gives you the direction of the strike too. Now the hinge zone is the area that had a plastic response to the stresses produced due to the tectonic activity or the minor actions. Now, this is the hinge zone only is the place where the plastic response of the long-term loading happened. Going back, if you see, there's a load that was produced, and there was a strain. Stress and strain, we call it. Let's call it in an easier way, the load and the deflection. So the load was given, and this deflected in this way and retained its original position, or yielded its original position over here. So the hinge zone is denoted as denoted the physical property of the rock that yielded for a long-term loading. The next is the axial plane. Now the axial plane is the imaginary plane line that gives you the the hint to the stress, where the stress was applied. Now, looking back in this place, you can see the hinge lines over there. This is the hinge point. Over here is the hinge point, and this is actually the axial plane over here. It's imaginary. Over here is the hinge line, over here is the hinge line over there, and this is the axial plane of the fold. Over here the axial plane is very tilted, uh, like this, and the hinge is this, and the hinge zone you can see. So each fold that you define is actually having the hinge zone and the axial plane and the hinge line. And next, the last is the limb. Limb is the follow-up of the fold, like just like a hand. So if there's a head over here, the hands are like this. So these are the limbs of the geologic folds. Now the first type of geologic fold that we'll study is the anticline. You can see over here, when the pressure is applied, it folds like this. It's kind of a GIF over here that I found on internet, very relatable. The pressure is applied over here on both side, and the fold was created. First kind of fold that we'll understand, or the first type of fold that we'll study, is the anticline fold. In anticline fold, these are the type of arch-like shape and has the oldest bed at the core. Now, if you see, this was the first bed that was created, and the oldest bed is at the core over here, like so. This was the oldest bed. So this was the oldest bed. So again, you see over here the hinge point, the axial plane, and also the limb over here, and this is the oldest core of the fold. Now, a typical anticline is a convex up. You can see it's a convex up, and in which the hinge or the crest is located at the curvature of the where curvature is the greatest. The limbs are side of the fold, and the dip always from the hinge. Okay. Now, if we go in this place, we can see the dip of the tilted bed, and also the strike. We can know this is very relatable now. Anticline can be recognized and differentiated from the antiforms, and the sequence of the rock layer and become progressively old towards the center of the fold. So whenever we see any anticline fold, you can always understand the core is the oldest bed. Even when you put a core, when you put a or you take out this core, actually you will get this. This was the oldest bed. Second kind of geologic fold is the syncline. Now it's very opposite to the anticline. Over here you can see the anticline and you can see the hinge line, but the syncline is kind of a valley of the of the of the of something, or the mountain. It's kind of a depression over here. This is the oppression. This is kind of a embedded point over here, and this is a depression point over here. Now you can see this is called the syncline fold. Over here in this rock, it was taken from the USA, the Interstate Highway 68, the road cut over here at Maryland, USA. You can see the syncline rock over here. A lot of time it's mistaken because you can say, hey, this is the fold. The mountain is actually the fold, but no, the mountain doesn't tell you the fold. The impression on the mountain will tell you what kind of fold is this. You can see a very beautiful syncline fold over here, and this fold is actually on the top. Now, if you see the core of this the core of this syncline fold is actually the the youngest. Now, if you see, if it's the youngest rock, and the hinge of this fold will have the oldest rock. So it's been overturned like a syncline, overturned syncline. Over here we have a beautiful anticline and syncline combination on this Great Canyon place. We have the anticline over here, the syncline. You always judge the anticline and the syncline by the layers or the sediments that were formed once the strait, but when the pressure actually happened, uh, it was folded either anticline or syncline. Over here, it's a wonderful combination of anticline and syncline. Then there are other kind of folds. There are symmetrical folds, which is very symmetrical to each other. You can see it's very parallel. It is going very parallel, and there are asymmetrical fold. Now, whenever you see a fold, you will always understand, or you'll always try to make sure one thing, that what kind of force must have been acting over here. Now, if you imagine, you always imagine. I always was one. I've always had a good time at our one of our professors class, one of our professor who teaches structural engineering, uh, Elvin sir or Vikas sir, wonderful teacher. They both will make you imagine about some force that is happening. Now, in the same way, if you put mechanics over here, you will always try to witness what kind of force must have created this kind of structure. And that's why the symmetric fold actually tells you the symmetry had the both the ways. There was a similar kind of fold, or equal, very equal kind of forces that acted, that made the syncline, made this syncline fold as a symmetric fold. And there was unsymmetric fold also, like over here it's parallel though, but you can see here it's a parallel fold, but it's not symmetrical. Somewhere it's large, somewhere it's strong. So now you can say that the left side or the right side, uh, the stress that this rock was subjected to was was not very symmetrical or was not equal, and that's why the asymmetrical fold is created. In the same way, we see isocline fold over here. Isocline fold is kind of fold that has a very rectangular, or sorry, very how do we say, very oval kind of structure over here. So this actually makes you know that the sediments over here was not that um, elastic. It had a very good plastic formality or disformality over here, and made this structure seems like this. The pressure happened to be equal maybe, or this structure was made overturned. You can see how now all these things actually overturned or recumbent or chevron folds. You can see all these folds actually will always tell you something, the history about it always will speak out to you. Just if you stand over here, one time actually one of my professor, geology professor from Bangkok, he actually was telling us a story that he stood at these kind of mountains and just try to notice what kind of a force would have been uh, would create to this kind of structure, what kind of sediments would have been deformed like this, what kind of what happens when these sediments are deflected like this, how these overturning folds are formed, how these recumbent folds are formed, how this is very pointed, why the hinge is very pointed over here, and did not fracture. If it would have fractured, it would have been a different kind of structure. Now, these all kind of folds over here will always tell you one thing, that these these fold were subjected to kind of a pressure. It was a long-term pressure. It will always tell you that these sediments actually were subjected to the pressure, and this pressure made these sediment to deform plastically, and not towards a fracture point, but towards a point where it remained like this. So it retained its deformed state, did not go back to its original place, but it retained its deformed place. That means the pressure actually created this. Next, we go through is the geologic faults. Geologic faults is now we come before that we studied the folds. Folds are actually not fractured, but it formed and retained structure. But over here, the geologic folds or the geologic faults are actually the fractured zone. Now, rather than deforming, these these were fractured, and because of the fracture, there was a block of rock that one came down and one remained at the original place. Faults actually allow faults allow the blocks to move relative to each other. Now, if you see these blocks, actually will always you will always see these blocks actually have moved relative from each other. This can happen because of earthquake or form of creep. Creep means it maybe because of some disturbance that happened and it slided down. And the faults may range in length of thousands of kilometers. Over here we see a big landscape, and in this big landscape we see this fault over here, and this fault actually is a different kind of fault, and it will make you know. We'll also study about some mechanics over here also. Then the geologic fault we have to understand first before we go into any types of geologic fault. We have to study about what kind of terms to use in this geologic faults. Firstly, you have to understand that to understand these faults, you have to understand terms. What is the footwall or what's the hanging wall? They look the same. If you look at the back one, what's the footwall and what's the hanging wall? It looks the same. So to understand that, we have to have some rules and regulations to define these kind of things and the fault planes and these terminologies that we'll go through. So first of all, you have to understand what's the hanging wall. Hanging wall is the, you have to understand two parts where you can define the hanging wall. First of all, to understand the hanging wall, we have to imagine there was no fault. So this is the place, there was no fault over here, and before the fault happened like this, one that remained at the original position was the footwall. It retained its original position, but one that came down was the hanging wall, the wall that hangs down. So you have to just imagine just the wall that hangs down. So there's two personification that I took: the wall that hang down and the footwall looks like a shoe. uh, the foot you put in the shoe. So anyway, it looks like a shoe. The footwall will always look like a shoe, and the hanging wall will always hang from the footwall. And the second characteristic is that this angle over here, you see this angle at the hanging wall will always be less than 90 or 90. So rarely it will be 90, but mostly it will be less than 90. And the angle over here at the tip of the footwall will always be greater than 90. So less than 90 hanging wall, greater than 90 uh, footwall. So always remember two characteristics: shoe, you put foot in the shoe, that's why it's a foot wall, and the hanging wall is kind of a wall that hangs down or hangs up. uh, so that's what, because whatever we'll define, whether it's normal fault or the reverse fault, normal fault will always, they both will be defined through the difference between the structure and difference between the footwall and the hanging wall's position. Now, the normal fault is a type of fault that is a result of tension. Now, you can see this rock form or this surface was actually subjected to the tension. Tension means there was force pulling them apart, and when they were pulling them apart, the footwall remained at this original position, and the hanging wall slided down, and that's how you will understand. So, in the normal fault, always the hanging wall will go down and the footwall will remain its original position. And this can be actually understood by the fault plane and the fault trace over here. So this is the fault trace and will always make you know. So maybe you will have just this part of this part of this thing uh, coming out of the ground. You cannot see these layers actually. So you will always define the fault by the fault trace and the fault plane. You will say that this is the hanging wall surface, and this is the, oh sorry, this is the footwall surface, and this is the hanging wall surface. But a lot of times when you cut the rock down, like this lady is standing over here, it's a very big fault. You can see this lady is so small over here, and this wall actually has come down. This is a normal fault. Always remember that two key points: tension is the reason of the normal fault, and also the hanging wall will go down and the footwall will go up or retains its original position. Second kind of geologic fault is the reverse fault. Now the reverse fault is actually very reverse of a normal fault. Now you see, and like in normal fault there was tension that was subjecting, but in the reverse fault there's a compression that's happening, because of which they oversides each other, and due to compression the hanging wall goes up or comes closer to each other, goes up against the footwall and leaving the inverse dip direction. Over here there's an inverse dip. Over here you have the dip and the strike, but right over here is the inverse dip, and inverse dip also has a direction, and inverse dip also has an angle that will go in negative. So over here we see the same example, the sediments that are over here, the layer that is over here. has gone up, the hanging wall has gone up. Always remember about the this thing here. If you see, if this is the the hanging wall, then it has the angle less than 90. Over here the angle is more than 90. This is the footwall, looks like a shoe, and the hanging wall that hangs over here. Reverse fault, you can see the hanging wall goes up, the hanging wall, the angle over here is less than 90, the angle over here is. So always whenever you see a fault, don't be confused that what kind of fault it is, whether it's reverse uh, or the this thing, reverse or normal fault. Don't be confused, because it's very easy when you look at the footwall and the hanging wall. But if you don't have the concept of footwall and the hanging wall, you'll always be very confused of what kind of fault is this. Now also we can understand the part where the tension is happening and the compression. These are kind of forces or the stresses that are acting over here. And we can understand over here that these walls over here that has gone up and gone down, footwall is was subjected to kind of a compression, and that's why these wall actually was the compression or the tension was so much that these walls actually went against the shear forces of this whole body, and the shear was happening. This is a very true example of shear force or shear stresses. So the shear happened, and the footwall and the hanging wall defines about the fault. Now always remember one thing. Once what I said was, you never build a house on this plane, these kind of planes, or you never build a building on these kind of planes, because it will always have a wrong effect. Because whenever compression these places never remains a very obedient place. If you build a house on this top, some or the other day it will slide, and there will be a problem in the construction. So geology actually puts a very important part. Now the last type of fault that we'll understand will be the strike slip fault. Strike slip fault is a very big fault compared to the normal and the reverse faults, because it sometimes happen on a very big plane. You can see this map. This map would have been, there are mountains in this map, and you can see the topography of this map. You can see the sea over here, and there's a fault that happened over here in this line, and this fault is kilometers uh, in range. So fault line, actually look at this farm. Maybe a earthquake or a tectonic activity had happened over here, and this made this this farm to look like this. It was actually having this way, but after the fault, strike slip fault happened, you can see this fault has actually uh, discontinued these lanes over here. So the strike slip fault usually happens because of a tectonic problem or tectonic movement. So anyway, if you're standing here, this is the right and the left, and if you're standing here, this is the right and the left. The last topic that we'll go through will be the unconformity. Unconformity is a very nice topic and a very geologically sound topic, because here you can go through the depth of the history of any profile. Over here you can see that there is a fold, and on the fold there is sediments that happen. Now if you understand the unconformity, you can always see that these folds happened before. This is the oldest, like rejoining in back. This is the oldest core, and this is a fold. This is the hinge, axial line. Everything happened, and after this force happened, a long time after that, even the sediments are formed over here. You can see these unconformities. So just to go through, unconformities are buried erosion, non-depositional surface separated by two rock masses of the strata of different ages. Now you see the ages are very different. It did not happen just a day after the fold happened. No, it took a lot of time in and we studied about the geological time. So each layer of this rock will always tell you something about the age of the rock. Now this is the younger layer, and then when we go through and study about these things, study about the unconformities, you will always understand the age of that sedimentary rock, or what kind of rocks, or maybe metamorphic rock, or the different kind of rocks underlying. Now there are three types of contacts. This is not the type of confirm unconformities, but this is a type of contacts of unconformities. So first of all, it's a depositional contact. There's a sedimentary layer deposited over the pre-existing rock. So over here you can see this fold, and this fold actually was created, and after that this is the deposition that happened. So this is a depositional contact. Also this kind of depositional contact usually. Fault contacts. Now this is a fault contact. The fault have happened over here, and after the fault, after this fault, actually the layer start depositing on here. So this is a fault contact. And intrusive contact, the one body cuts over another, also kind of a you can understand intrusive contact. Next is the type of unconformity is a disconformity. Now disconformity are usually erosional contacts that are parallel to the bedding upon the lower unit. Now you can see over here that this was the rock. This was the rock that was there. The sediments was there, and this eroded firstly, and after erosion, again the deposition started happening. So firstly, there's a erosion that happened on this kind of rock, and after the erosion, the sediments again tried to. So you can always indicate the length of time that actually was there. Now, for erosion of some rock takes a lot of time. If you put a stone over in your field or in your garden, it will not erode in 1 or 2 days, or not even 1 year. It takes a lot and thousands of years for erosion over here, or weathering of the rock. But after weathering, there is something that happened. Maybe some or the other way, the deposition started happening, and the deposition was made on this block, and this is called the disconformity. Angular unconformity. Angular unconformity, this is a very good diagram that I found on internet. There was this, it starts from here. The deposition happened. After deposition, there was a uplift and the tilting because of some geological activity or tectonic activity that happened over here. So this deposition was tilted, and after tilting, the upper layer was eroded, and after erosion the deposition started happening again after thousands and thousands or millions of years, and that's how we get the angular unconformity. That means there are some steps over there. In disconformity, the tilting did not happen. So when if would have been this layer, if would have been tilted, it would have become the angular unconformity. But the tilting did not happen in disconformity, and unconformity, the tilting happened. So deposition, uplifting and tilting, erosion happened, and then the deposition of the next layer started, and so we get the angular unconformity. And the last topic of today would be the non-conformity. Non-conformity is also a kind of it's different from disconformity and angular unconformity, because this disconformity is a sedimentary rock over the sedimentary rock, and angular angular unconformity is also the sedimentary rock, uplifting, erosion, and sedimentary rock. But in non-conformity, there is some different kind of rock over here, and some different kind of rock over here. Maybe this is the uh, This is maybe the igneous or metamorphic rock, and over there the sediments started, and the sediment actually made was eroded over here, and then sediment started cementing and stratifying, and so we get the different kind of the unconformity, that is the non-conformity. Over here you can see this is igneous rock or metamorphic rock, and on that the sediments started happening, and same as here, this is a wonderful igneous rock, and on that the the sediments started happening. So hope you understood this kind of uh, problem. Now you can know what is a strike and depth, strata, fold, and unconformity. Joints we'll study in different section, and also you understood the classification of the of this. So if you have any doubt, please ask me through mail, or else please search by yourself, because there's a lot of material on the internet too. Right now, as in this time we are using the internet, please do try to understand by that. Hope you have had a nice lecture. Thank you.